Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we are discussing about solid mechanics and materials subject. So in this subject, today we will see the Eulers column theory. So what is this theory and then what are the applications of this Eulers column theory and then how to derive the Eulers equation for different end conditions of the columns we will see in this talk. So first of all, the course outcome of this topic is analyze the Eulers column theory and the deformation of columns and struts. So how to write the equations for different columns and struts, and so how to analyze the column theory equation, the derivation part we will see. So introduction part. So what is this Eulers? So what is the importance of this theory in solid mechanics and materials? So the structural member subjected to an axial compressive force is called a strut. So as for definition, a strut may be horizontal, inclined, or even vertical. So example, connecting rod and piston rod, etc. So take one structural member. It may be vertical or horizontal. So one end is fixed. So this member subjected to compressive load, that is P, towards its axis, that is axis parallel. So subject to an axial compressive force. It may be horizontal or inclined and vertical. But vertical strut used in buildings or frames is called a column. It may be horizontal and it may be vertical. So the pillar between the roof and floor, those struts are called as columns. So short length, those structures are having a short length, that is called as struts. Having long lengths, that is those those structures are called as columns. So length, the length of the structure will be high. So example, pillar between the roof and floor. So now we'll discuss about failure of a column strut. When it will fail. So it has been observed that when a column or strut is subjected to some compressive force, so the compressive stress will be induced. So that is sigma is P by A, that is compressive stress is load per area. So where the compressive force P and A is the cross-sectional area of the column. If the force or load is gradually increased, the column will reach a stage when it will be subjected to the ultimate crushing stress. It has been observed that when a column or strut is subjected to some compressive force, see here the force, compressive force given and cross-sectional area. So the force or load is gradually increased up to ultimate stage. That stress is called as corresponding ultimate crushing stress. So beyond this stage, the column will fail by crushing. So the load corresponding to the crushing stress is called crushing load. A compression member does not fail entirely by crushing but also by bending. So that is buckling. So this happens in the case of long columns. So all the short columns fail due to their crushing. But if a long column is subject to a compressive load, it is subject to a compressive stress, the fail due to their crushing. So at which the column fails, that corresponding stress is called as crushing stress. That load is a crushing load. But always not fails due to this crushing. Sometimes the columns fails due to the bending. That phenomena is known as buckling. So generally happens in long columns. The short columns are fails due to their crushing, and long one fails due to the buckling. Here shown some diagrams. The actual failure of a column or a strut. See, you can see here buckling load. This one also, the column fails. The column between the filler and the roof. Here you can see. So if the load is gradually increased, the column will reach a stage when it will start buckling. The load at which the column just buckles is called buckling load or critical load or crippling load. And the column is said to have developed an elastic instability. For a long column, the value of buckling load will be less than the crushing load. So moreover, the value of buckling load is low for long columns and relatively high for short columns. So the buckling load is very low for long columns, high for short columns. See here shown the failure of column or stud, buckling and compression and shear. So you can see here failure of a column after the buckling. So now we will discuss about Eulers column theory. So the first rational attempt to study the stability of long columns was made by Mr. Euler. He derived an equation. So that equation is called as Euler's equation for the buckling load of long columns based on the bending stress. How to calculate this buckling load? So up to now we have discussed about buckling load. Due to the buckling load, the column fails. So what is this buckling load? How to calculate? How to avoid? So while deriving this equation, the effect of direct stress is neglected. This may be justified with the statement that the direct stress induced in a long column is negligible as compared to the bending stress. So direct stress, the load per area, direct compressive stress. So we are not considering. So this induced in a long column is negligible as compared to the bending stress. So assumptions in the Euler's column theory, the following simplifying assumptions are made in the Euler's column theory. Initially the column is perfectly straight. and the load applied is truly axial. The cross section of the column is uniform throughout its length. The column material is perfectly elastic, homogeneous, and isotropic, and thus obeys Hooke's law. So you know Hooke's law is stress is directly proportional to strain. And also you can, with the help of Young's modulus, E into epsilon. So these are the assumptions made while deriving this Euler's column, Euler's column theory. So one is initially the column is perfectly straight, and the load applied is truly axial loads only. The cross section of the column is uniform throughout its length. There is no deviation. The column material is perfectly elastic material. It should be follow the Hooke's law and homogeneous and isotropic material. And the length of the column is very large as compared to its cross-sectional dimensions. The shortening of column due to direct compression, so being very small, so that is neglected. The failure of column occurs due to buckling alone. So these are the assumptions. And for derivation part, the sign conversions are also very important, though there are different signs used for the bending of column in different textbooks. But in subject point of view, here commonly used the internationally recognized signs are given here for positive and then negative. For negative is called as concavity, and the positive is convexity. So shown here different shapes here, positive sign and negative sign. Whenever it occupies the shape concavity, so you have to use negative sign. For this convexity shape, positive sign. While solving the problems, you should use these sign conventions. Next one is types of end conditions of columns. Very, very important, these end conditions. So based on these end conditions, we will derive the Euler's theorem. In actual practice, there are a number of end conditions for columns, but we shall study the Euler's column theory on the following 4 types of end conditions. So, which are important from the subject point of view. One is both ends hinged. Second one is both ends fixed. One end is fixed and other end is hinged, and one end is fixed and other end is free. So 1, both ends are fixed, 2 and 3 and 4. So these are the end conditions. So based on these end conditions, we will derive this Euler's column theory by using boundary conditions. So first we will see the columns with both ends hinged condition. So in this, consider a column AB of length L hinged at both of its ends A and B, and also carrying critical load of B. I will show you the diagram. As a result of loading, let the column deflect into curved form AX1B. Now consider any section X at a distance small x from A. So this is the given column with both ends hinged, A and B. So initially that is AX B. So after deformation AX1B. So here the column deflect into a curved form AX1B as shown in figure. So for section X with the distance small x and length also given, the axial load shown here. So let P is the critical load on the column, and then deflection of the column at X, Y, that is small y. The moment due to critical load P the moment is minus p into y. So minus sign due to concavity towards initial center line. So already you have discussed about sign conventions. The concavity always negative sign have to use, and convexity positive sign. So now the columns with both ends hinged condition derive the equation. So you know the bending equation. So already we have derived m by I is equal to sigma by y is equal to E by R. So now take this equation and then write down the equation a into d square y by dx square plus p into y is equal to 0. So now in this you can write this equation d square y by dx square plus p by a into y is equal to 0. So for auxiliary equation m square plus p by a is equal to 0, m square is equal to minus p by a. So m is equal to minus p by e I. So now the roots are m is equal to the general solution for the complex numbers. Write down. So the m is equal to in the complex number alpha plus or minus I beta. So here write down the solution for this above equation. E alpha x into c1 into cos beta x, c2 into sin beta x in terms of c1 and c2. So therefore y is equal to c1 into cos beta into x plus c2 into sin beta into x. So here p by ei is the m. M is equal to alpha plus or minus I beta. So where C1 and C2 are the constants of the integration. So you have to calculate the C1, C2 by using boundary conditions. We know the boundary conditions are when x is equal to 0, y is equal to 0. The equation 1 we get C1 is equal to 0. Similarly, when x is equal to L, y is equal to 0. Therefore, the equation again change it into this second equation. 0 plus C2 into sin L into square root of P by E. Because C1 is equal to 0. Now, the third equation we will get C2 into sin into L into P by E. So, from this equation C2 is equal to 0 and then consider C2 be equal to 0 and as well as C1 is equal to 0, then Y is equal to 0. It indicates that the column has not bent at all or bending of the column will 0, but it is not true. So the sign of L square root of P by EA is equal to 0 and L into square root of P by EA is equal to 0, pi is equal to 2 pi is equal to 3 pi. So taking the least significant value. So then you will get Euler's equation. L into square root of P by EA is equal to pi. So squaring on both sides, L square P by E I is equal to pi square. So P is equal to pi square E I by P L. Sorry, pi square E I by L square. So this is the final Euler's equation. See, like this, need to derive the Euler's column theory for different end condition. We have seen only one condition, so that is both ends are hinged and length is L and load axial load P. So in this manner, you should calculate, derive the Euler's theory for different end conditions and apply boundary conditions, you will get equation. This equation is called as Eulers load theory, or the buckling load or critical load. So these are the references I have taken. Ramamurthu. The title of the book is 10th of Material. Publishers are Dhanpati Rai and Publishing Company. And R.K. Bansal, Textbook of 10th of Material. And R.S. Kurmi, Strength of Material. And publishers are Chand and Co. So these are the references I have taken for this PPT. So you can refer any one textbook for more information. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.